Number 22A. Distinguish between diffusion and effusion. So now we're getting into section 4 content, diffusion and effusion. Words sound very, very similar. They are related, but they do have a couple of key differences. And so you need to be able to tell the difference between the two. So distinguish. Diffusion occurs when two gases mix. Okay, and so for diffusion to happen, there has to be at least two gases present. There can be more, there can be 3, 4, 5, however many you want, but there has to be at least two. If there's only one gas present, you might say, is it not diffusing across the room? No, we just call that expanding. It's going to expand to fill its container. When there are two gases, quote unquote, expanding, we call it diffusion. Now, diffusion specifically involves at least two gases mixing by random molecular motion. So this kind of goes back to the assumptions of the KMT, right, and ideal gas behavior. But effusion, remember, it's different, even though they do have some related ideas. Effusion occurs when a gas under pressure passes through a tiny opening, a small opening. And so diffusion, there is no pressure. It's simple, random molecular motion driving the mixture of at least two gases. Where effusion, again, there is random molecular motion here, but the gas is under some sort of pressure. Again, the way I always picture it in my mind is a bike tire being punctured. We all know that a bike tire needs to have some sort of pressure, right? And when you pop that tire, the gas leaks out. So that gas has to be under pressure. Now, when you puncture a bike tire, the tire doesn't explode. There's just a small hole, a tiny opening through which all of that air, all of that gas is going to escape, right? Releasing all that pressure, making it so you can't functionally use that bike anymore. B, at a given temperature, what factor determines the rates at which different molecules undergo these processes? So again, referring to diffusion and effusion. So at the same temperature, and so when we say at the same temperature, what we're telling you is that there is no difference in kinetic energy. Kinetic energy has to be the same. And so when kinetic energy is the same, and that means that the expression, if you remember, kinetic energy equals 1/2 mv squared. When there's no difference in temperature, that means there's no difference in kinetic energy. And so if we have two different gases, we know that the average kinetic energy of the system is the same. And so since two sets of kinetic energies for two different gases are the same, we get to set these equal to one another. So you guys have seen this because you've definitely watched the video lecture. Well, sorry, that's V. And of B, velocity of B, we get to use this version of the equation. We get, instead of kinetic energy, because average kinetic energy is the same for these two gases, that means that overall these two equations are equal to one another. And this is actually the basis of Graham's law, to be honest. We have to do a little bit of deriving, but this is the basis of Graham's law. So again, at the same temperature, so kinetic energy is equal. That means that we get to set these two equations equal to one another. Okay, the heavier molecule will have a lower average velocity than lighter molecules. Why? Because when this m value starts to change, this v value, the velocity, is going to have to change to accommodate for that change. This is an inverse proportionality because they're being multiplied by one another, right? Mass multiplied by velocity. And conversely, the heavier, so not conversely, as an extension, heavier molecules diffuse and effuse more slowly than lighter molecules because they're moving around slower. And so they're going to pass through, for the example of effusion, they're going to pass through that small opening a lot more slowly, at a slower rate. And so, again, like I've already mentioned, the rate varies inversely with the square root of the molecular masses, which is Graham's law.